Look at a modern advanced fighter jet in action. Its lethality relies entirely on its ability to outmaneuver, out-target, and outstrike anything in the sky. This diagram of a precision-guided munition shows exactly how performance is achieved. Deep inside the weapon, laser seekers depend on ultra-pure neodymium and yttrium, while high-temperature fin actuators require samarium-cobalt magnets to function during supersonic deployment. These materials are separated rare earth elements. The Government Accountability Office has repeatedly issued severe warnings regarding these materials. The United States currently imports over 95% of these refined rare earth compounds, with the overwhelming majority originating from or being processed in the People's Republic of China. If that single foreign supply chain is severed, the United States military loses the high-purity oxides and permanent magnets required to build or maintain its most critical weapons platforms, from the F-35 Lightning to Virginia-class submarines. A persistent narrative suggests the world is simply running out of rare earth elements, and that the United States is geologically starved of these crucial materials. Geological data proves otherwise. The United States holds millions of tons of economically viable rare earth reserves. At sites like the Mountain Pass mine in California, the ore grades and contained tonnages rival some of the largest deposits on Earth. Yet, despite sitting on vast domestic resources, America still ships its raw, mined mineral concentrates overseas, remaining entirely dependent on geopolitical rivals for the finished, defense-grade materials. Midstream chemistry, rather than mining, serves as the primary industrial bottleneck, the complex process of separating intermingled rocks into individual, high-purity elements. Possessing a massive geological endowment offers zero strategic value if a nation lacks the specific industrial infrastructure required to refine those minerals into a usable form. To understand why this chemistry is so difficult, we have to look at two adjacent elements on the periodic table, neodymium and praseodymium. These elements are trapped in a physical phenomenon known as the lanthanide contraction. Their deeply buried 4f electron orbitals fail to shield the nucleus, meaning their outermost valence electron shells are virtually identical. In a water-based solution, they both lock into the exact same +3 electrical charge. This bar chart compares the physical and thermodynamic properties of both elements. Looking at the ionic radius column on the left, the size difference between a neodymium ion and a praseodymium ion is a microscopic 1.6 picometers. That's a variance of barely 1%. Because their sizes and electrical charges overlap so completely, you cannot use standard chemical reactions to separate them. If you try to precipitate neodymium out of an acid bath, the praseodymium will simply fall out right alongside it, fitting perfectly into the exact same crystal structure. It is the chemical equivalent of being handed a bucket of identical twins and asked to sort them based exclusively on a 1 millimeter difference in height. Standard chemistry fails entirely. The industry's answer to this atomic deadlock is a brute force, continuous flow method called multi-stage solvent extraction. An acidic water solution heavily saturated with mixed rare earths is pumped into a vat alongside a highly flammable kerosene-based organic solvent. Inside, these two naturally repelling liquids are intensely agitated by mechanical impellers, forcing them into a chaotic microemulsion. Dissolved within that kerosene are specialized organophosphorus molecules, carbon-based compounds that contain phosphorus, acting as chemical hooks. Because of that tiny 1.6 picometer difference in size, these hooks will preferentially bind to neodymium just a fraction of a percent more often than praseodymium, pulling it across the liquid boundary into the oil. The turbulent mixture then flows into a quiet settling chamber. Governed by gravity, the lighter oil floats to the top, carrying its slightly neodymium-enriched payload, while the heavier water sinks. This schematic maps the true scale of a commercial solvent extraction facility. To achieve a 99.5% pure split between neodymium and praseodymium, this mixing and settling must be repeated sequentially across 50 to 60 interconnected stages in a continuous countercurrent flow. Exploiting a subatomic measurement requires tens of miles of piping, millions of liters of toxic solvent, and massive fire mitigation systems. This immense physical and mechanical burden creates a staggering barrier to entry. Throughout the late 1990s and early 2000s, Western nations largely abandoned this specific chemical ecosystem. The capital costs of building these sprawling cascades, combined with the severe ecological toll of managing highly saline, radioactive wastewater, pushed the industry offshore. This chart compares global geological reserves against actual refining capacity. While reserves are spread across the world, China controls roughly 91% of the planet's rare earth separation capacity. They absorbed the massive environmental externalities and utilized heavy state subsidies to build a processing monopoly. This dominance relies on a strategy called ecosystem lock. By controlling the vast majority of active refineries, state-backed enterprises can intentionally suppress the global price of separated oxides, operating at margins so thin that any new Western separation plant becomes immediately unviable for private investors. A mountain of domestic ore is strategically inert if it must be shipped entirely through a geopolitical rival's chemical plants just to be fashioned into the permanent magnets required for a U.S. weapon system. Recognizing this profound vulnerability, the Department of Defense is now aggressively intervening. Utilizing Title III of the Defense Production Act, the Pentagon is actively forcing the reshoring of midstream chemical separation. Since 2020, over $400 million in federal awards have been deployed to domestic commercial entities. The goal is to establish fully sovereign, mine-to-magnet supply chains entirely on American soil, independent of foreign export controls. However, this transition faces severe headwinds. Constructing hazardous chemical separation facilities, navigating strict environmental permitting, and training expert hydrometallurgists takes years, leaving the defense industrial base acutely exposed in the near term. Achieving total supply chain autonomy for the most critical weapon systems depends on whether the United States can rebuild the industrial infrastructure to master this specific, unforgiving atomic chemistry.